All right, if you're gearing up for an embedded systems interview, you know there are a few questions that are pretty much guaranteed to pop up. Well, today, we're tackling the big one. We're going to give you the master key to understanding the C program memory map. So let's get right into it. Just imagine it. You're sitting in the interview, and that is the very first question they ask. It's a bit of a beast, right? But don't worry. By the time we're done here, you're going to have a rock-solid answer that'll absolutely impress them. You've got to think of this memory layout as the fundamental map of the whole system. Seriously, knowing this map shows that you understand how your software actually lives and breathes on the hardware. It's the bridge between your code and the silicon. So let's walk through it. Okay, first things first, the absolute basics. A microcontroller has two main kinds of memory. You've got flash, which is non-volatile. Think of it like a book. Even if you close it and turn the power off, the story is still there. Then you have RAM, which is volatile. This is more like a whiteboard. It's your program's temporary workspace. But as soon as the power goes out, poof, it's wiped clean. So let's take a tour of that map. Your actual compiled code, what we call the .text section, lives in flash. Same goes for any constant data, that's .row data. Pretty much everything else happens in RAM. You've got .data for your global variables that start with a specific value, .bs for the ones that just start at 0, the heap for memory you manage yourself, and finally the stack for all your local function variables. We're going to dig into each one. Now, almost every single time, an interviewer is going to start by asking about the stack and the heap. Think of this as level 1. It's the most common challenge, and it's designed to see if you grasp the real-world trade-offs of how memory works. And here it is, the classic follow-up question. The thing is, the stack grows downwards from the very top of RAM, while most other things, like the heap, grow upwards from the bottom. They're like two trains on the same track heading right for each other. So what happens when they finally collide? Well, that crash is what we call a stack overflow. It completely corrupts your data and brings your system down. And it's almost always caused by one of two things. First, you've got infinite recursion, a function that just calls itself over and over and over, piling up data on the stack until there's no room left. Or, second, you just try to declare a ridiculously huge local variable, like a giant array that's just too big to fit. This table really breaks it all down. The stack is completely automatic. The compiler handles everything for you, and it is blazing fast because adding or removing memory is just a single CPU instruction. The catch? The data only lasts as long as the function is running. The heap is the total opposite. It's completely manual, it's way slower, but data you put there sticks around until you say so. But all that control comes with some big risks. And in embedded systems, those risks are a huge deal. If you forget to free memory, you get a memory leak that slowly eats up all your available RAM. Then there's fragmentation, which is when your heap gets broken up into a bunch of tiny, useless little pieces. But the biggest deal breaker, especially for real-time systems, is that using the heap is non-deterministic. You can't predict exactly how long it'll take to run, which is a massive no-go in anything safety critical. Okay, you've passed level 1. Let's move on to the next path. If you nail the stack and heap questions, the interviewer is going to pivot. They'll want to test how deep your C fundamentals really go. This is all about where your variables truly live. So they might show you a little piece of code, something that looks super innocent, just like this. It's just a function with a simple counter. Now, you just finished talking about how local variables live on the stack, right? Well, they're setting a trap. And there's the question. So where is this counter variable stored? Your first thought is probably the stack, right? I mean, it's declared inside a function. But look really, really closely at that one little keyword in front of it. Static. Nope, not the stack. That static keyword changes the entire game. It tells the compiler that this variable's lifetime isn't just for the function call. Its lifetime is the entire duration of the program. It needs a permanent home. And since the stack is temporary, it gets placed in the data segment right alongside all the other initialized global variables. Okay, so that brings us to another great question. Both .data and .bss hold these permanent global-style variables. The only real difference is that .data variables have a starting value, and .bss variables are just initialized to 0. So why bother having two separate sections? Why not just merge them? The answer is all about saving precious flash space. It's a clever optimization. Look here, if you declare a big 1,000 byte array without any initial values, it goes in .bss. Now, it'll take up 1,000 bytes of RAM when the program runs, for sure. But look at the flash usage, it's basically 0. The system doesn't need to store 1,000 zeros in your program file. It just makes a little note to itself to set aside that space at startup. But check out what happens when you initialize that array. It now lives in .data. It still uses 1,000 bytes of RAM, but now, bam, it also uses 1,000 bytes of flash. Why? Because the program file now has to physically store every single one of those initial values. So by separating .bss and .data, we avoid bloating our program with huge blocks of useless zeros. It's a really smart trick. So, if you've made it this far in the interview, you are crushing it. This final path is the boss level. These are the advanced questions that really separate a good candidate from a great one. This is all about the tools that work behind the curtain to make this all happen. I mean, think about it. This whole system doesn't just happen by magic. How does the program know where RAM even starts? Who tells it where to put the stack? And what in the world is running to get everything ready before your main function is ever called? The answer is this amazing duo. First, you have the linker script. It's the map or the architect's blueprint. It's a config file that tells the tools exactly where flash and RAM are and which sections go where. Then you have the startup code. This is the janitor or the setup crew. It's a little bit of code that runs before main, reads that blueprint, and does all the setup work. It copies the initial values for .data from flash into RAM, and it wipes the whole .bs section with zeros. And one last absolutely crucial piece of the puzzle is the volatile keyword. See, your compiler is really smart, and it loves to optimize your code. If it sees you writing to a variable twice, it might just get rid of one of them. But what if that variable is actually a hardware register? Volatile is your way of telling the compiler, hey, back off. This memory location can be changed by hardware at any second, so you are not allowed to optimize any of my reads or writes to it. Do exactly what I say. Okay, let's bring this all home. You've navigated the different paths, you've seen the traps, and you now have the complete picture. Let's put a bow on this and look at the whole map one last time. And here it is. Flash permanently holds your code in .text, your constants in .row data, and the initial values for your .data section. Then, at runtime, RAM comes alive. You have .data and .bs for your globals at the bottom, the heap growing up from there, and the stack growing down from the top. That is the entire map in a nutshell. So after you've laid all this out perfectly, the interviewer might lean back and hit you with the final question. Okay, so what? Why does knowing all this actually matter for the job? And this right here is your knockout punch. It matters because it proves you're thinking about more than just code. You're thinking about efficiency, because every single byte of memory counts on a microcontroller. You're thinking about reliability, because you know how to prevent system crashing bugs like Stack Overflows. It proves that you understand that deep fundamental link between software and silicon. It shows you're not just a programmer, you're ready to be an embedded engineer.